And then we have a relationship where we have sigma A squared minus sigma A sigma B plus by sigma B squared must be less than sigma U squared. Okay. So I want you to look at this relationship now. Okay. I want you to look at this relationship now. So the next thing I'm going to do is we're going to sketch the operating boundary of von Mises criteria. And at the same time, I'm going to also sketch out Tresca criteria, which we learned on Tuesday. Okay, so we're going to sketch them out first. Okay, so on x-axis is sigma A. On the y-axis is our sigma B. Okay, so x-axis is sigma A, y-axis is sigma B, and then over here, these are our stress U. Okay, this is also our stress U. This is our minus stress U. This is our stress U. So the first thing I'm going to sketch is I'm going to sketch Tresca criteria first, which we learned on Tuesday. Okay, so we're going to sketch Tresca. Okay, so this is Tresca condition or criteria. Okay, so the pink is our Tresca. So the structure is deemed safe is within the pink line. Okay, so I'm going to call this based on Tresca. Okay, Tresca, which is based on maximum shear stress. Okay. Next, I'm going to draw von Mises. Okay, I'm going to sketch von Mises. Okay, so this is von Mises. And you realize that von Mises criteria is look like an ellipse. Okay, it looks like an ellipse. So the blue is von Mises. Okay, which look like an ellipse. Okay, so why does it look like an ellipse? Okay, and mathematically there's a reason for it. Okay, so if we look at the parent function, okay, of the ellipse shape, right? You have x squared over a squared plus by y squared over b squared, and this thing is equal to 1. Okay, so this is the parent function of an ellipse. Okay, So if you have b squared x squared plus by a squared y squared, and over here you have a squared b squared, this will be equal to 1, right? Then if you have b squared, wait, you have b squared x squared plus by a squared y squared, and this is equal to a squared b squared. Okay. And then when you bring it over, you have b squared x squared minus by a squared b squared plus by a squared y squared is equal to 0, right? So if we were to, our x-axis is sigma a, our y-axis is sigma b, so we have b squared, right? Sigma a squared minus by a squared b squared plus by a squared sigma b squared is equal to 0. Okay. So if you look at this equation over here, right, it's very similar, right? It's very similar to what we have in over here. Okay, they are very similar. So if you were to plot this on Excel, right, you will get an ellipse, right? Now, I would like to highlight 4 points. Okay, I'd like to highlight 4 points now, comparing Tresca and Formesis. Okay, so let me label the 4 points that we are going to look at. Okay. So I'm going to draw a exactly 45 degrees line. Okay. And we are going to look at point A. Then we are going to look at point B. Okay. And then we are going to look at point C. Now, point C, right, will intersect Tresca criteria and Vomisis at different locations, and also point D. Okay, so 2 point Ds is along the red line. Okay. So if we were to compare Tresca and Vomisis, there are some similarities and there are great differences also. Okay, as you can see, the shape is not the same. So we are going to look at Tresca, and then we're going to have Vomisis. So if we look at point A, right, we realize that stress A is equal to stress B is equal to stress U. For Vomisis, it's also the same, right? So stress A is equal to stress B is equal to stress U. Then we look at point B, right? You have stress A is also equal to stress B is equal to minus stress U. Likewise, on Vomisis is also the same. Okay. So these two conditions is where Tresca and Vomisis are similar. Okay. But now I want to turn your attention to point C, right? So at point C, stress A, so you have minus stress A is equal to stress B, and this will be equal to minus stress U. Oh, sorry, 0.5 stress U. On stress A, yeah, 0.5 stress U. if we were to look at vormesis, right, at point C, which I'm highlighting in yellow now, the point C for vormesis and Tresca did not overlap one the other. Okay. However, minus stress A is still equal to stress B, and this is equal to 0.577 stress U. Okay. And you realize that in Tresca is 0.5, vormesis is 0.577 of the yield. Means vormesis will generate a higher magnitude, right, of stress A, stress B. And likewise, if we were to look at point D, right, if we look at point D, you will have stress A is equal to minus stress B, and this is equal to minus 0.5, right? Point D, you will get minus 0.5 stress U. Am I right? At point D, you have stress A. No, hold on. It's still 0.5, not minus. And if you look at minus stress A equal to stress B, sorry, stress A is also equal to stress A equal to minus stress B. Now this will be equal to 0.577 stress U. Okay. So now the thing is this, okay? Why 0.577, okay, stress U at point C and point D, right? So let's look at the conditions, right, at point C and point D for vormesis, okay? Right. So at point C and point D, the conditions are where sigma A is equal to minus sigma B, or minus sigma A is equal to sigma B, right? So if we were to substitute sigma A is equal to minus sigma B, okay, into equation number, where equation was that? We're going to substitute into equation equation 1, okay? Sorry, not equation 1. We're going to substitute into, I'll call this equation number 3. Okay, if we substitute this into equation number 3. So we substitute into equation number 3, right? So we will have, so equation number 3, let me write this out, is sigma A squared minus by sigma A, sigma B, plus by sigma B squared. And this is equal to sigma U squared. Okay. So the one I'm going to choose or substitute, okay, I will do the other way, do apologize, where we have sigma B is equal to minus sigma A. Okay. So sigma A squared minus by sigma A multiplied by, so B is equal to minus sigma A, plus by minus sigma A squared. This will be equal to stress U squared. Okay. So when you square everything, minus minus become plus, is 3 sigma A squared is equal to sigma U squared, right? So sigma A is equal to